start by considering the Pantheon. The Pantheon, a temple to all the gods, was built around 126 AD after a previous temple on that same site was destroyed by fire. It was probably designed by an accomplished Roman engineer named Epolodorus of Damascus, who's known to have designed several other monumental Roman structures that were built around the same era. When we look at the Pantheon from the front, it looks just like a traditional Greek-style temple. But beyond that portico is something very different. The main sanctuary of this temple is a circular plan with an inside diameter of 142 feet. And overhead is an extraordinary concrete dome of that same diameter. At 142 feet, it was by far the largest dome of antiquity, but it was also the largest dome in the world all the way up to the 19th century. Now, the structural system of the Pantheon consists of just two main elements, the dome itself, and then the cylindrical wall, which we call a drum, which supports the dome from below. That drum, the cylindrical wall, is 21 feet thick, and its interior face is punctuated first by the main entrance to the sanctuary, and then by 7 large niches or indentations that are evenly spaced around the circumference of the interior wall. From a structural perspective, those niches are important to us because they represent places where the wall was much thinner than the normal 21-foot width of the remainder of the drum. Now, like Roman arches, the dome was constructed on temporary wooden centering, temporary shoring that held it up while construction was in process. And that centering was used to form the spherical shape of the dome, and it was also used to create those really interesting rectangular indentations on the inner surface of the sphere. Those are called coffers. And finally, the centering was used to form the most distinctive feature of the Pantheon, that circular opening at the very top of the dome called the oculus. Now, in general terms, here's how that structural system works. The weight of the dome, which is considerable, it's about 5,000 tons of concrete, is transmitted in compression from all the way up on top, the oculus, downward along those meridional lines to the base of the dome where it rests on the drum. And the drum then has to transmit the full weight of the dome plus its own self-weight straight downward into the building's foundations, while also restraining that tendency of the dome to expand lateral, the horizontal thrust that we just saw in my demonstration. To make this system work, Epolodorus had to overcome 3 major challenges. First, he had to restrain that lateral thrust. Second, he had to design the dome such that it would be able to carry the hoop stresses that occur about 1/3 of the way up from the base. And finally, he had to devise a way of transmitting all of that weight downward through the drum without crushing the niches, which are located at places around the perimeter of the drum where the walls are considerably thinner and therefore more vulnerable to overstress. Epolodorus handled that first challenge, containing the lateral thrust, first and foremost by making the dome as light as possible. Now, as you can see in this cutaway drawing, the dome tapers significantly. It's 21 feet thick at its base, and it tapers down to only 4 feet thick at the top near the oculus. The oculus itself, as well as those coffers we looked at earlier, the rectangular indentations, further reduce the weight of the dome by replacing concrete with empty space. But perhaps the most innovative aspect of the dome design was Epolodorus' selective use of lightweight aggregate in the concrete. Now, as you'll recall from our lecture on engineering materials, aggregate is just the stone substance that's mixed with cement and water to create concrete. What Epolodorus did in the design of the dome was to vary the type of aggregate in order to better suit the structural purpose of the concrete at that specific location within the dome. The dome was constructed in layers of concrete, and at the lowest layers, all of the aggregate that was used to make the concrete is broken brick. It's very strong, but it's also relatively heavy. Higher up in the dome, the brick transitions to greater use of tufa. That's a porous limestone rock that's much lighter than brick. And then at the uppermost layers, close to the oculus, all of the aggregate in the concrete is an extremely lightweight volcanic pumice stone. Now, both tufa and pumice are nowhere near as strong as brick, but up near the top of the dome, strength really isn't as important. as it is down at the base. And so Apollodorus was very carefully tailoring the material to its structural purpose. One modern study of the dome of the Pantheon concluded that the use of lightweight aggregate alone reduced the stresses in the dome by over 40%. This sort of specialized use of lightweight aggregates, which was common in Roman structures, wasn't used again until the 20th century in construction engineering technology. It's really quite amazing. The design of the drum also reflects Apollodorus' careful attention to the challenge of containing that lateral thrust delivered to the drum from the dome above. That circular configuration of the drum is inherently resistant to overturning, much more so than a column or a flat wall. The walls themselves are quite thick, and you'll note from the cutaway drawing that they extend upward well above the base of the dome in order to increase weight. As we've seen in previous lectures, both width and weight both increase the stability of a structure against overturning. Apollodorus handled the challenge of transmitting vertical load downward through the drum by using a device that we've also seen in previous lectures, the relieving arch. Here you see the relieving arches. If you look closely, you can see them on the surface of the outer walls of the drum of the Pantheon. What you can't see is that these relieving arches are located at the same locations as the niches are on the inside of the building. So these are the areas where the exterior walls are actually much thinner than 21 feet, and the relieving arches channel that tremendous weight of the dome safely around the niches and then directly down to the building foundations. And how did Apollodorus handle the hoop stress in the dome that occurs at a maximum about 1/3 of the way up from the base? Well, what he did was to add extra weight to the lower portion of the dome all the way around the outer perimeter to prevent that bulging effect that we saw in my earlier demonstration. In this 3D model of the Pantheon, you can see that added weight of concrete in the form of those stepped rings that are provided around the outer circumference of the lower third of the dome. These provide the stabilizing function of closing up the gaps that you saw forming between those meridional segments in the demonstration that I did a little bit earlier. Now, before we leave the Pantheon, I've got to answer that question that's been on your mind for the past several minutes. How does the oculus work? And after all, if each meridian in a dome behaves just like an arch, then how can these arches be carrying load when their keystone is missing? Well, to understand the answer to this question, you need to look at the dome not as if it were a two-dimensional arch, but rather as a full three-dimensional structure. If you look closely on this model, you'll see that the outer perimeter of the oculus is reinforced with a ring of bricks called a compression ring. The compression ring is really fundamentally a three-dimensional keystone that just happens to be hollow in the middle. It's really a wonderful detail that reflects a keen understanding of the mechanics of a dome. Clearly, Apollodorus of Damascus knew what he was doing.